Welcome to the week number 11, Fundamental of Econometrics. Before going for the formal content of week 11, it would be great that I finish the content of week 10, which was remaining. So in week 10, we were looking into the multicollinearity, the consequences of imperfect multicollinearity. Then we saw an example. We talked about the detection of multicollinearity. So this was the component which we covered last week. Now I'm going to talk about very quickly the remedial measure of multicollinearity, and then in particularly I'm going to focus on the principal component analysis. We are going to see how we can perform this principal component analysis in eViews, and then we'll quickly summarize the entire multicollinearity topic in one slide. So let's start. So this was the last slide which I covered in the last lecture of week number 10. I already told you how we can do remedial measure for multicollinearity, and we did discuss that in principle we shouldn't be doing anything because we have no control over data. However, a few things which econometricians used to do to solve the problem of multicollinearity include the redefining of the model by excluding the variables that are causing the problem of multicollinearity. However, such solution also solve the problem of multicollinearity but cause another problem which we call specification bias that should also be avoided because it's also one of the major assumptions of ordinary least square method. Then finally we were talking about principal component analysis. So this the first part of this lecture is discussing the principal component analysis as a remedial measure for multicollinearity. Second part of the lecture would be the start of the formal material of week 11 and the introduction to new topic. So let's start principal component analysis. What is principal component analysis? It's a procedure that can be used to remove multicollinearity from a data. So it's one remedial measure, one proper remedial measure. Principal component analysis construct artificial variable called principal components from the regressor such as they are orthogonal to one another. Now again a new term, principal components or PCs. So first we start with artificial variable. Principal component analysis is a procedure that helps you to remove multicollinearity from your data. How we do that? Instead of using the original explanatory variable, it creates the artificial variables. It tells you that don't use this explanatory variable, create an artificial variables from your explanatory variable that has a problem of multicollinearity. Use that variables, create new variable which we call artificial variable or components, principal components, and use that principal components in your model. And that will solve your problem of multicollinearity because these principal components will not correlate with one another, or they will be orthogonal. So what is orthogonal? In literal meaning, it refers to creating a right angle. This is when the two variables are not correlated with one another, they create a right angle on a graph. So that's why they are called orthogonal. So you can just ignore that. You can just say a principal component analysis is based on construction of artificial variables, and we use that artificial variables because these artificial variables do not correlate with one another, or it does not violate the assumption of multicollinearity. So in the principal component analysis, the advantage is you remove the multicollinearity from your data, but the problem is the interpretation of the coefficient on the principal component analysis is not straightforward, and or it's not clear till now. So that's the cost you pay for applying this method. So again, summarizing, we have a problem of multicollinearity in our data. We want to remove that. Multicollinearity shows that your explanatory variable are correlated with one another. So you can remove that through PCA method. What does PCA do? PCA create artificial variable based on your correlated variable. They create new artificial variables which we called principal components, and we use that principal components in our regression model rather than using the original variable. And by this method we remove the multicollinearity from our data. However, it comes at a cost, and that cost is that we cannot interpret that principal component like we do interpret the coefficient of a regression model. So let me do that. I will be going to explaining the theory, which I did already, and I will be demonstrating that how to perform this PCA. However, going beyond that, going more in detail to the methodology is beyond of this course scope, so I wouldn't be going there. So how to perform PCA? The basic idea I already told you, that we create the artificial variables based on the existing variables in our model. So we are going to group the correlated variable into subgroups. So we create correlated variables subgroups so that the variable belonging to any subgroup have a common factor that move them together. So we create subgroups of correlated variables in such a way that there is a common factor that move with these variables. So it's like some variables are correlated, so we create a subgroup of that and we identify a factor that move with these variables, and we use then that common factor instead of the original variables in our model. So for example, we have a model, we have 10 explanatory variables in our regression model, and these variables are strongly correlated with one another, and we identify that there is a problem of multicollinearity in our model. Now we want to apply PCA to this model to remove that multicollinearity. So how we can proceed? First of all, we can look into the correlation matrix, which we saw last time, how you can generate that in eViews. So you will be getting 10 by 10 matrix here because you have 10 explanatory variables. So you will be getting by 10 by 10 matrix with diagonal all 1 that will be showing you the correlation matrix, and that will be you will be seeing a lot of high values of the correlation coefficients for these variables. So once you have that correlation matrix, once you are clear that your data has a multicollinearity problem and you want to solve it through PCA, then you proceed for the applying PCA method. So we start with the auxiliary regression. The auxiliary regressions are used to create that subgroups which we were talking, or that artificial variables which we were talking about. So we already know what is auxiliary regression, right? Should I remind you? Auxiliary regression refers to when you regress one explanatory variable on the remaining explanatory variable. So let's say we generate a regression in which x1 is dependent variable and x2 till x10 are independent variable. That's the first auxiliary regression. Then we have a second auxiliary regression in which we regress x2 on x1, x3, x4 and all the other x variables. So that would be the second auxiliary regression. Similarly, we can think of the third auxiliary regression in which we have x3 as dependent variable and all other x variable as independent variable. So we use these auxiliary regression to create the principal components. How we do that? Once I will show you that in eViews how we do that. Once we have these, once create these species or these principal component, we use these principal component as an explanatory variable instead of the original x variable to explain the dependent variable. So let's say we had the model yi and it's explained by these 10 explanatory variables. We know these are multicollinear. So we construct the auxiliary regression from these variables and we replace these variables with that factors. So let's say I created 10 factors from these 10 variables. So we will replace that 10 factor here in this model and we will use that 10 factor as an explanatory variable instead of using this x1. So let's say I created one factor which I call PC1, PC2, PC3 and so on. Principal component 1, principal component 2, and I will replace these x's with that principal component and will run the model. So that would be solving the problem of multicollinearity through principal component analysis. Thus we help to explain the dependent variable yi with the help of PCs instead of x's. and these PCs are not multicollinear with one another. So I will show you that how we can apply that in eViews. So let me quickly do that. Now this is slightly complicated task, although there are a few clicks, but the output is very much detailed. Please pay focus and make sure that you apply that yourself. Again, I'm going to use the same data which I just used for VIF, the same 16 variables and the same model. I'm going to use the very same data. So we are going to apply PCA to this data. So how we do that? First, take the data. I will run the regression model first. Then I will freeze the record so that I have the results available to me. Then I will apply PCA in following steps. First, I will select all 15 independent variable and I will open them as a group. Okay, that's a straightforward task. Secondly, I will go to the view of the group and select the principal component. So I will go the variable are open as a group, so I can see the values of the variable. I will go to the option view, and if you see here, you will find a principal component option. I will just click on that. When it's open, there are a number of there is one separate window open which is called principal component window. There are a number of options on that. For time being, I will leave everything for default. I will just select one option, table, and I will leave everything as a default. I will press OK, and what I get is the output of PCA. Now there is a long output. I will freeze that all. I will just keep it. I want to generate one more thing and then we will discuss the output. So the second thing is I go again to the view. I again open the principal component window, the same window, but instead of selecting table, this time I select the option Eigenvalue Plot and generate a plot. I will select the option Eigenvalue Plot. I will press OK. It will give me a plot. I will save that plot as well. And I will keep that for discussion as well. Now, I will advise you again, freeze, stop this presentation or this discussion here. Download the data, go to eViews, perform these steps by yourself. Please generate these principal component analysis output by yourself, generate this plot by yourself, and then play the presentation for the next part. I will be demonstrating this. You can take 10 to 20 minutes for doing that. Now I will be presenting this output by myself, and we'll be showing you how to generate that, and then we will be discussing the output very quickly because we are short of time. So let me switch back to my eViews. So let me show you how we can perform principal component analysis in eViews. As I told you, first of all, we open all the explanatory variables as a group. So I will start with age of the female worker, her education, her experience, her family income, her father education, her husband age, her husband education, her husband hours of working, hours worked by labor. Female worker was a dependent variable, so I will exclude that because we are constructing principal component from explanatory variables. So I will just be selecting the explanatory variable. Husband wage, kids under age 16, kids between age 6 and 18, and then kids under age 6, then the wage of the female, then the mother education, then the marginal tax rate in the country of resident, and then the unemployment. That make it 15 variables. I open them as a group. So once I open them as a group, all the variables being visible, next I go to view, then I go to principal component analysis. And as I told you, there will be a new window, principal components. In this principal component window, I will be selecting just the first option, which is table, and I will press OK. When I press OK, I get this results, very nice tables, a very detailed result of the principal component analysis, which I'm going to explain you in a while. This table you can see here very clearly has three parts. The first one the middle part, which has the first part has a title of eigenvalues, then the loading, eigenvalues loadings, and then the ordinary correlation. I'm going to talk about it in a while. I will freeze this output here, and I will go again, view, and component, principal component analysis. This time I want to generate the graph of the eigenvalue. So I will select Eigenvalues Plot. I select keep other default option, I press OK, and I get this nice eigenvalue plot. So this is the principal component analysis in eViews. Now let me show you the interpretation of all these which we got. So let me switch back to my presentation. Let me start with the output which we just got. As you saw, PCA output was in 3 parts. So there are 3 parts. I will be going to discuss it one by one. I will start with the first one, which is the ordinary correlation. Then I will explain this, the last part first, then the first part, then the second part. So let me do it one by one. The third part, it's ordinary correlations. So we already know what is correlation. This part only shows the pairwise correlation among the explanatory variables. So nothing new. The diagonal are 1 because the correlation of age with age is 1, education with education is 1, and so on. And experience with age is 0.48, and so on. You have the interpretation for all the other member of this matrix. So I will move to the first part of this output, which was the eigenvalues. So take eigenvalue as synonymous for variance. So this graph shows the variation of each variables. There were 15 explanatory variables. So the first value 3.54 shows that what is the variation or variance in variable 1. So that was 3.5. Then we say that this part, variable 1 value 0.2363, shows that out of total variation of all 15 explanatory variable, 23.63 is explained by the first variable. If we take the second variable, its variance is 2.88, and it explains 19% of total variation of all 15 explanatory variables. So that's the interpretation for the second variable. And now the cumulative part. So the cumulative value, this 3.54 is the same. If I add 2.88, the value of the second, that make it 6.42. So the variation of the first variable is 3.544, and when I look into the variation of the second variable alone, it's 2.88, but the combined variation of first and second variable is 6.426, which we obtained by adding these two values. Similarly, for the third one, you add the first 3, and for the fourth one, you add another one in it, and so on. And the cumulative portion says that for the first variable, explain 23% of the total variation of all the explanatory variable. 23% is explained by first variable, 42.84 is explained by the first 2 variables, 52.57 is explained by the first 3 variables, and so on. So we can see that if we move to the 6th variable, about 75% of total variation is being explained by this first 6 variables. So that's the interpretation of this particular output. Now moving to the main crux, this is the PCA output analysis, and this is the eigenvectors loading. Now what does this show? This create 15 factors out of these 15 variables based on the logic of auxiliary regression, and these factors shows the weight of different variables in each factor. For example, the first, I think it's not very visible, so let me make it more visible. I'm focusing on the first 6 component for the reason that the first 6 variables explain about 75% of total variation, which we saw just on the previous particular slide. So that's why I'm focusing on the first 6 components. So let me take this to the next slide. Now, if we look into here, the first principal component gives a weight of 0.005 to the variable age, 0.3827 to education, and so on for all. Similarly, the second component, it's again a new artificial variable generated from all these 15 variables assigning different weight. This PC2 moves together with these variables. So we converted these explanatory variables to artificial variables or subgroups which is made of these variables but different variables which are not correlated with one another. So if we look into PC1, the first, these are the weights, different weights assigned to each variable in construction of the first component, and we can see here that the PC1 has major weight assigned to education. For example, education here is 0.38, then education again for the father education 0.26, then the mother education 0.22, and similarly I think the husband education is 0.36. So the education has the major chunk in this particular principal component. But if we move to the fourth principal component, PC4, we see here that 0.71, which is the highest weight, that's for the husband hours worked. So you see every component or the artificial variable being generated has a different combination of weights for each variables. Now, principal component analysis, if we go one step back and think about principal component analysis method. Principal component analysis method generate artificial variables that are made of the original explanatory variables, and we use them as a substitute for the explanatory variable. So these principal PCs are the artificial variable generated out of the explanatory variable which was strongly correlated with one another, but now we created artificial variables which are not correlated with one another. Now this sounds very interesting, this sounds very elegant when you look into the mathematics, when you look into the derivation of all that, but the interpretation is subjective. Interpretation is complicated. For instance, if we look into the PC1 first, we see here that education being the most dominant one, so I may call this that PC1 is the education level. But someone else may say, no, the family income has a weight of 0.424. So why not we call it, wage has 0.23, so why not we call it an income with components rather than education components, so that make it subjective. Similarly, once we do all that, we can then use these PCs instead of the original variable. So let me put it more in a bigger picture. We started that we want to model hours as a function of these 15 variables listed in this particular slide. Now these variables were multicollinear with one another, so instead of using these, we says that we apply principal component analysis and we generate artificial variables which we call principal components, and we will be using these principal component instead of the original variable to remove the problem of multicollinearity. Why we use PC1? Because these PC1 are not correlated and it represents the same variables. So that helps for us. So we use these variables and we can, but then there are questions here. One question is that there were 15 PCs. How many PCs we are going to use? 5, 6 or 7? This is kind of subjective again as well. A graph of eigenvalues can give us some values that below this red line or up to this red line we can stop here at 6 or 5 and can use that as an explanatory variable in our model. So going back, we have 15 new variables which we can use in our model. So how many we use? We think of 5 or 6. Let's go for 6. The next step is how we are going to run this model. So for that, well, the problem with eViews is we have to run this model, hours being function of PC1, PC2, PC3 till V6. So we have to run that model. The problem with eViews is that eViews do not have the capability, built-in capabilities of running this model. So we can't do this analysis further in eViews. However, we can use some other software such as Minitab or Stata, but I am not going to do that. So I'm not going to burden it with you or with all this further detail. So I will ask you just stick to what we have. I will just take the output to just give you the idea that this model could be run in Stata or in Minitab. This is Minitab output shared by Gujarati, so I took that output as it is. And as you can see here, ours is regressed on the components, the components which we created, PC1 till PC6. And you can see here that the coefficients are statistically significant only for PC2 and PC4, whereas PC1, PC3, and PC5 and 6 are statistically not significant. So that's our conclusion at this stage, that while performing principal component analysis, the two components PC2 and PC4 are the more prominent component, and we can look into the weightage of that, and we can tell that which particular variables are prominent for explaining the worked hours of the female worker. But this principal component analysis help us to remove multicollinearity from our data, but the problem it generates is that it is at the cost of not being able to have a good interpretation of our model. Let me put it in more easy words. When we run a regression model, so we interpret the coefficient as, for example, this minus 1.49, we will interpret it as 1 unit change in PC1 will bring 1.49 change in hours worked. But what is 1.4? What is PC1? Is PC1 education? Is PC1 wage? Is PC1 something else? Now that's the cost you pay for applying PCA. PCA don't have any clear interpretation. You cannot separate the different variables from which this PC1 is constructed. So in principle, you solve the problem of multicollinearity, but at the cost of not having any interpretation of the PC1, PC2 or all other PCs, because we cannot separate the effect of each variables. If there is something prominent, you can say that for example, when we saw the PC1, the education was prominent, so you can up to some extent say that the education is the prominent one, but apparently someone may disagree with that as well, rightly disagree with that. So that's the cost you pay for PC analysis. According to Gujarati, if we can identify PCs with some economic variables, the principal component analysis become more useful and can be helpful to solve the problem of multicollinearity. Now, to summary and conclusion, well, in this particular topic, it was a very lengthy topic. Apparently, was not 2 lectures were not sufficient to cover that. But anyhow, we discuss what is multicollinearity. We discuss it, the theory of it. We discuss it, the consequences of multicollinearity, that how it affects the variance and how it has the consequences for the t-value or for the hypothesis testing. We then discuss that how we can identify the existence of multicollinearity in our data. What are the symptoms of it? We did talk about auxiliary regression. We talked about the variance inflation factor. We saw how variance inflation factor can be calculated. What is the interpretation of that? And then we discussed the solution of multicollinearity, that how we can solve that. We did agree that in principle nothing could be done because we can't change our data. We also talked about it, if we drop the variables which are causing the problem of multicollinearity, that can solve the problem, but it's lead to another problem about which we have to be careful. So if we drop a variable, we can be misspecifying our model. So we have to be very careful when we are dropping a variable just because of multicollinearity. And then we talk about principal component analysis, that how principal component analysis is helpful in removing multicollinearity. Principal component analysis, in very brief words, help us to identify factors that are made of the explanatory variables with a different weight assigned to it. And these factors replace the original explanatory variables in the model. These factors are not correlated with one another, and these factors substitute for the explanatory variable, and we run the model, and that solves the problem of multicollinearity, but at the cost of lesser economic meaning or interpretation. Okay, so that was the principal component analysis and the topic of multicollinearity. So let me start the week 11, and the topic for week 11 is heteroscedasticity. As I already told you that heteroscedasticity topic will be covered in 2 weeks. So in first week I'm going to talk about what is heteroscedasticity, what causes heteroscedasticity, and then obviously what are the consequences of heteroscedasticity, and we are going to see some example from the data using e-views that how we can look for heteroscedasticity. Well, we are going to discuss test for heteroscedasticity in the next lecture, and in the next week we're going to see the remedial measure for heteroscedasticity. So let me start with the topic heteroscedasticity. This is chapter 4 in the book, the textbook we are following, Econometrics by Example, written by Dominic Gujarati. So let me start with the basic assumption of ordinary least square method. I showed you this slide many times. There are 7 basic assumption of ordinary least square method, A1 till A7, and as I told you earlier as well, that according to Gauss-Markov theorem, if these 7 assumptions are met, the ordinary least square estimators are blue, or best linear unbiased estimator. For heteroscedasticity topic, we are going to focus on A4 assumption, that's on homoscedastic or constant variance, and we says when this assumption violate, we are confronted with a problem which we call heteroscedasticity. So before proceeding to this topic further, let me revise the concept of heteroscedasticity. We did discuss this concept briefly in the time when we were discussing the assumptions of ordinary least square method. However, I will quickly review this topic, this concept again. So one of the assumptions of classical linear regression model was that the variance of the error term is constant or homoscedastic. Now I can recommend you, if you have issues with understanding the basic OLS assumption, please switch to week 3, lecture 5. That may help you to give you an overview. So let me highlight how these homoscedastic assumptions work in particularly. So I will start with example of considering 2 variable y and x, where y is a dependent variable and x is independent variable. I am considering variable income and saving being function of income. So in general, we would expect when income increase, the saving will also increase. That's a general behavior. So now in case of homoscedasticity, what we would expect that when saving increase, the variation in saving would be of the same nature with increasing income level. Let me put it in more simple words. We say that when income increase, the saving will increase, but when the income increase with the different levels, the saving variation with income levels also remain the same. Or let me put it through a graph that will make it more simple. So in x and y axis, I have income and saving respectively, and I have the probability density function of the error term on the z-axis. Now we say that, let's say we have some income level. This is the curve or the line being fitted to the relation between saving and income, and as you can see in upward sloping curve showing that as the income increase, the saving also increase. Now if I take different level of income, let's say I take a level of income x1, x2, and I can think of many more income level as well. So our assumption is that the saving at income level x1 have the same variation as the saving of income level x2. Let's say I have 300 people about which I have the income and saving data, and let's say 100 people are with the income level ranging in X1, 100 people with income range X2, and 100 people with income level XI. So they are in this range. Some, for example, if X1 is $10,000, so 100 people in this range, some will have if it's 10,000, so some people will have 3,000, some people will have 4,000, some people 7,000, some people will have up to 10,000 is the maximum. Similarly, for 20,000 range, so we say it's between 10,001 till 20,000. So some people will have close to 10,000 value, some people will have up to 20,000, and some people will lie between these two ranges. And similarly for the third range as well. Now we presume homoscedasticity mean that the variation in the income range, the first one we define, the second one we define, the third one, and as many as we define, the variation of saving in all these ranging will be the same. Or in other words, if I put it in some graphical format, so we say that the variation of the predicted value of saving, or the variation or the variance of the error term during these interval would be same. So that's, if that's the case, we call it a case of homoscedasticity. Now, if this is homoscedasticity, what is meant by heteroscedasticity? So let me move to heteroscedasticity slide. In heteroscedasticity, again taking same example, same income level, but now we say that as income changes, the saving changes, and the variation in saving is different. For example, if you see here, the first or the lowest income level has lesser variation, so the distribution look different than when you look at the second income level and the subsequently much higher income level. So that's indicate that the people having higher income has much more variation in their saving compared to someone who is in the lower income level. On average, they have lesser income variation, saving variation. So that's a case of heteroscedasticity. You know, we see that here for a given value of x, the value or the variation of the predicted value of y, or the variance of the error term, is not same across each given value of x. So that's, we say, is that a case of heteroscedasticity. And we says that in this particular case, increase in income, saving also increase, but with higher income families save more and with a higher variability compared to lower income families, as is clear from their distribution as well. So we call this this case a case of heteroscedasticity, because saving increases but with a different variance for all level of income. Now going back to the original concept of heteroscedasticity, so now it should make sense to you that variance of error term given x value, so we took different level of income, different level of income or independent variable, and we saw the variance for each level, and when it remained the same, like for every income level, if the variance remain the same, so we call it a case of homoscedasticity. However, if this assumption of ordinary least square method or classical linear regression model does not meet or not satisfy, we call it a case of heteroscedasticity or unequal variance, and we denote it by sigma I instead of sigma. Why we put subscript? It should be sigma I and it should be sigma. So why we place the subscript? Because the reason is that I represent that the variance is changing, the variance or the error term variance is changing. It's no more constant, it's changing, it's different for different income levels, so I is changing. Now once we know the concept of heteroscedasticity, the next step is that we need to know why heteroscedasticity in the data happens. So that's important to know as well. Starting with the reasons, there are many reasons. Some of or major of these reasons are included here. We are going to discuss that one by one. So starting with the first major reason we can think of is the error learning models. Now, Well, you don't have to read or learn a new model. Just let me tell you by example that how it works. So, for example, we keep on saying this very famous saying, practice made a man perfect. And then if you think of, for example, learning typing, I don't know how many of you learn typing or if you know typing, but trust me, when you want to learn typing, you have to do a lot of practice. And only with practice you learn. Now, as we say that if you do more typing practice, you will have lesser typing mistakes. And then we can think of linking the heteroscedasticity concept with just this learning process. For example, if I take the same graph which we saw a while ago, so on x-axis I'm taking hours of typing practice as an independent variable, and y as the dependent variable, that's errors in typing. So if I do more hours of typing, I would be having lesser typing mistakes. So if I model this phenomena, and then I can see that initially when I have lesser hours of practice, when x value is smaller, so I have more errors, so my distribution is spread. But as I practice more and more, my mistakes will be reducing, so my distribution is kind of having a smaller variance and a smaller variance. So in that case, I can say that it's a problem of heteroscedasticity. If I have a data of this nature, so I would have a problem of heteroscedasticity. So we can say that, okay, if we have to model a data that is of such nature that it consists of having some learning process of this nature, we may think of having a problem of heteroscedasticity in these kind of models. So modeling a data that involves error learning kind of models would have the problem of heteroscedasticity. The second one is mixing observation with different measures of scale, such as mixing high income household with low income households. Now, we just saw when we were explaining, we were looking into the basic concept of heteroscedasticity, we saw that we combine different kind of household in the same data. We saw three levels of income with the low level of income, middle level of income, and the higher level of income. And we argue that as the income level increase, the variation in the level of saving also increases as you move from a low level of income to the higher level of income. Thus, while mixing observation with different measures of scales or mixing of observations which are of a different nature, and that automatically introduce the heteroscedasticity issues in your data. So a data consists of diverse groups or observation will have a problem of heteroscedasticity by default. Then we can think of improvement in data collection techniques. So when data collection techniques improve, like if you are collecting a data with one measure and then suddenly things improve, you collect the data with improved technique, so you may have a problem of heteroscedasticity. Or you can think of comparing two cases where in one case you have a data collection at a certain poor method and the other with a slightly better method, so you may expect a problem of heteroscedasticity combining these data. For example, here is an example. I try to put it in Pakistani context. So you can think of a competition between two banks, and then there is one bank which is called National Bank of Pakistan. That's a private, that's a government-owned bank. So it's the ownership of the government of Pakistan. And then I thought of including one private sector bank which is doing very well in private sector, and I put Mizan Bank, which is a premier Islamic bank in Pakistan and a leading bank in Pakistan at the moment. So if I compare these two banks and I put an argument that we says that when there is a sophisticated data processing equipment and then with a fewer errors being introduced while processing the data in their monthly and quarterly statement of their customers. So you would expect normally a lesser chances of heteroscedasticity in the data. But if you think of a bank which don't have such facilities, so normally you would expect a problem of heteroscedasticity in their data, or when you are combining these two kind of data, you will find a problem of heteroscedasticity. So you think of one bank, Mizan Bank, a better one with a better and sophisticated data processing equipment, versus the National Bank of Pakistan, which is the ownership of Pakistan, and maybe you have heard some scandals related to the bank, while they were unable to detect pensioner getting pensions while people were not there, or a kind of ghost pensions. So these kind of things happens, and then when these kind of things happens, you may expect the problem of heteroscedasticity. So moving back to my original slide where I was discussing the reasons for heteroscedasticity. So we look into the three kind of reasons modeling a data that require a model, a sort of model based on error learning models, and then you can think of mixing of different kind of observations with the built-in problem of heteroscedasticity or diversity, and then you think of using data collection techniques being improved versus poor data collection techniques. Then you can think of presence of outliers in your data. So sometime when you are collecting the data, outlier may also cause a problem in your data, problem of heteroscedasticity. So let me again refers to what is an outlier. So in generally when we have some data and then there may be some observations that is either very small or very large compared to the rest of the sample, so we call such observation or such value of the data as an outlier. This is very common. In generally, outlier do influence everything in your data. For example, think of your own class. If the entire class marks are close to 70% and someone score 99%, so the overall class average will get disturbed with this outlier. So outlier do influence everything, all other values in the data. Normally averages are very sensitive to outliers. So in generally we can say when there is an outlier, it can cause heteroscedasticity. So consider here is an example of the stock prices and the consumer prices. The stock prices is represented with the Y and the consumer price or consumer price index with X, and that's for the period post-war World War II period for 1969, and then it's for 20 countries. So let me show that graphically. On y-axis we have stock prices, and on x-axis we have the consumer prices, x variable. And when we plot this data, and you can see all the combinations of x and y values are more or less in the range of 9 and you can say up to 20. And then you have one observation which is for country Chile, and you can see here this is close to 25 and 26. So this is a kind of an outlier. So outlier in this particular case is this country, and this introduction or including of this outlier in the data would cause heterogeneity in our data. So, and then we may think of heteroscedasticity caused by specification bias. I think specification bias should be clear to you as well now, but since we studied it some while ago, so we will quickly tell you. Normally we say that when there is in specification bias, it introduces heteroscedasticity. Specification bias is because of two reasons. We are going to see that in more detail at a later stage, but for time being we can think of the specification bias being caused either by excluding some important variable which we call omitted variable bias, or when we do specification bias because of incorrect functional form of the model. Instead of using log you use linear, or instead of linear you use log. That kind of things also introduce heteroscedasticity. So Here I included two examples. The first example is, for example, I want to model the demand function for a particular commodity, but I do not include the commodities that are complementary or that are competing goods in my model, in my regression model. So that would introduce automatically the problem of heteroscedasticity or the constant variance. So normally when we model a demand function, we think about the commodities that are competing commodities, or we can say the substitute, and also the commodities that are complementary or that are used along with that particular commodity. So the prices of these commodities are also important, because the demand of a particular good will be linked with the commodities that are either substitute with it or complementary with it. So excluding these kind of variables from your model will introduce a problem of heteroscedasticity in your regression. If we exclude these variables, it will cause the heterogeneity, but if we include that, it may disappear. So that's one reasons for heteroscedasticity. And then we can think of the incorrect specification form as well. For example, instead of using log lin, we use linear, or instead of using linear, we use log lin or double log model. That may also introduce a problem of heteroscedasticity in our model or in our analysis. So these were a few reasons for heteroscedasticity. The last one is incorrect transformation of the data. Now that's a bit tricky in a sense that we haven't studied till now what do we mean by the transformation of data. But well, I will just tell you briefly, and a later stage when we are going to study time series analysis in our I believe in 15th or 14th week, then we are going to talk about it in more detail. So normally, if I put it in very simple word, data transformation refers to the use of transform form of original variable in the model. Now, econometricians use these transformations, or economists use these transformations to solve a problem of autocorrelation, which we are going to study next week most of the time, or make the data more smoother. So if I put it in a more simple words, data transformation is a way of transforming your original variable to a new form. For example, instead of using normal variable, we use its lag value or its first difference rather than using the original variable. And why we do that? We do that to solve some problem. Now, obviously, I used the two terms. One I called the lag, and then the other one I called difference. So this is the two famous kind of transformation which we use while doing econometrics analysis and modeling. Lag refers to when you use the lag value of the variable instead of the variable itself. Like, what would be the lag? For example, if I have a variable yt, so yt is the y value measured in period t. So instead of using yt, I use yt minus 1. So I call this a lag variable. So yt and then yt minus 1. So instead of using the y variable measured in period 1960, I use the y variable measured in 1959. So I will call it a first lag. Then I can think of a second leg as well. Then I can think of a third leg as well. We will see that when we study the time series topics at a later stage. But at this stage, I can tell you only that much, that instead of using the original variable, you use its transform form. Similarly, difference refers to when you take a difference yt and you subtract its previous value from it, yt minus 1. So we call this the first difference. So that's the first difference. So we can think of the second difference. We can think of, normally we use first or second difference. And similarly for the leg, we can use, for the leg, we don't use just two legs. We can think of even 5, 6, 10 or 12 legs, depending upon the nature of the problem. So these are the two very traditional way of transforming the data. And we do that to solve a problem of autocorrelation or most of the time and make our data stationary. These are technical terms or jargons associated with time series analysis. We're going to see that at a later stage. But here the point is that if we do incorrect transformation, this may cause the problem of heteroscedasticity. So here I give an example. For example, instead of using the per capita GDP, instead of using GDP, or using first difference of variable instead of original variable. So first difference, I already explained you what does first difference mean. Instead of using y variable, the income variable, you use its first difference. So you subtract y in period current minus y in the previous period. You use the first difference, or you use the GDP per capita instead of GDP. So these are kind of transformations, and obviously it changed the interpretation of your variables, but at the same time it do help you to solve problems of for example autocorrelation, or gives you some more interesting information. But at the same time, incorrectly done, these transformation can introduce the issue of heteroscedasticity into your data, as per David Henry, a well-known renowned world econometrician. He says when you do these incorrect kind of transformation, that can lead you to the problem of heteroscedasticity. So these were some highlights of what can cause heteroscedasticity. So we mentioned 5 or 6 reasons that can lead to the problem of heteroscedasticity. So this is the end of this lecture. I hope this was a productive session for you to know how what heteroscedasticity mean, and what are the causes of heteroscedasticity, and how it happens. If you have any question, feel free to write me in email and ask your questions. And if you like the video, please do like and subscribe our channel. Thank you.